On the 3rd of June in 1920, Ernest Rutherford gave a lecture to the Royal Society in London describing his nuclear model of the atom. With it, Rutherford explained how all of the elements of the periodic table were composed of only three building blocks: the proton, the electron, and an as-yet undiscovered particle that he called the neutron. Atoms were assigned an atomic number based on the number of positively charged protons in the nucleus. The number of protons and neutrons jointly accounted for most of the mass of the atom. The much lighter electrons encircled the nucleus in equal numbers to the protons so as to neutralize the electric charge, and electrons populated energy shells in a way that explained the periodicity of the periodic table. The discovery of the neutron in 1932 was the clinching proof of Rutherford's model. Today, we'll see how that model became the foundation of the atomic age, but the next generation of scientists would soon come to realize that the ultimate answer to what matter was made of was far more complicated than Rutherford could have imagined. Welcome to Atomic Universe. I'm Dan Bergstrom, material scientist. It's kind of amazing when you think about the experiments described in our last episode, which revealed the protons and neutrons hiding deep inside atoms, and realize they were all done with scientific equipment that could sit comfortably on a tabletop. The key ingredient used by all of them was an alpha particle emitter, which probed the atom's interior. Alpha particles scouring off of gold reveal the nucleus inside the atom, alpha particles fused with nitrogen nuclei to release protons, and alpha particles reacted with beryllium nuclei to release neutrons. The natural alpha radiation used in these experiments had energies between 4 and 8 million electron volts. An electron volt is the energy it takes to accelerate the single charge of an electron or proton across the electrical potential of 1 volt. Alpha particles had enough energy to initiate certain nuclear reactions, such as those that allowed for the discovery of protons and neutrons, but it wasn't enough energy to reliably smash atoms into pieces and really probe what else might be inside. This work was also time-intensive due to the rate of alpha particle emission from natural ores being somewhat slow. So early nuclear physicists were well motivated to find or develop intense sources of high-energy radiation to speed up their work. At Cambridge's Cavendish Lab, 2 projects were about to do just that. The year is 1932, and James Chadwick had just discovered the neutron, confirming Rutherford's prediction from a dozen years earlier. But it was only the first of 3 major breakthroughs in this golden year for the Cavendish. The second of these breakthroughs was the splitting of the atom, a project that had started 3 years earlier when English physicist John Cockcroft had talked the frugal Rutherford into buying a 350 kilovolt transformer for artificially creating high-energy particles. Over the next few years, Cockcroft, along with Irishman Ernest Walton, achieved even higher energies with the help of a voltage multiplier of their own invention. By 1932, after some successful trials, they were ready to demonstrate the device to Rutherford. The device, taking up most of a lecture hall, had a tall column configured to accelerate protons in the form of hydrogen ions up over 400,000 electron volts. These protons were directed at a lithium target chosen with the hope that its light atoms could be smashed apart relatively easily. At the bottom was a small observation hut, which had a scintillation screen and a Geiger counter for detecting any particles emerging from the lithium target. As one observer reported upon seeing the equipment energized, "Lightning crackled and flashed as high-tension spheres sparked. A tall glass pillar glowed with a luminous blue haze. Presently there was a clicking sound, and a counter began to clock in the fragments of the splitting atoms." They had started to detect particles as the acceleration potential exceeded 125 kilovolts. At 400 kilovolts, there were many hundreds of particles per minute. Rutherford himself then squeezed into the small box with the scintillation screen to see the particles with his own eyes. After being helped to his feet, he declared, "Those scintillations look mighty like alpha particle ones, and I should know. I was there at the birth of the alpha particle, and I've been observing them ever since." Later experiments confirmed that these were indeed alpha particles, that is to say, helium-4 nuclei. They were produced via a nuclear reaction where lithium-7 absorbed a proton to briefly become beryllium-8 before disintegrating into 2 alpha particles. In other words, Cockcroft and Walton's particle accelerator was the first machine to split the atom. The protons had an incoming kinetic energy of 400 kiloelectron volts, or keV, and the 2 alpha particles produced were measured at a combined kinetic energy of about 17.2 million electron volts, or MeV, for a net gain of 16.8 MeV. If we calculate the mass-energy balance of this nuclear reaction and allow for measurement error, this result was a good match for the theoretical value of 17 MeV given by E equals mc squared, providing the first experimental confirmation that mass could be converted to energy according to Einstein's famous formula. In parallel with Cockcroft and Walton's work on accelerating protons to high energy, elsewhere at the Cavendish, Patrick Blackett continued to work with natural sources of radiation. Back in 1924, Blackett had used his cloud chamber design to capture the alchemy of alpha radiation transmuting nitrogen into oxygen. In 1932, he would adapt his design to make that year's next big breakthrough, the discovery of antimatter. Hot air balloon studies in Austria, conducted by Victor Hess in 1912, had shown that high-energy cosmic rays from outer space are continually hitting the upper atmosphere, ionizing the air they travel through. Working with Italian Giuseppe Acciolini, Blackett developed a new cloud chamber design featuring a system of Geiger counters that could trigger cameras automatically whenever these cosmic rays were detected transversing the chamber. With this setup, they were able to capture pictures of cosmic ray events about every 2 minutes. The cameras captured streaks of water droplets condensing around ionized atoms created by the path of any fast-moving charged particles. From their previous work, they could easily recognize the characteristic tracks of protons and electrons. By seeing what thicknesses of lead were required to stop these particles, they were able to estimate their energy as being tens of millions of electron volts, orders of magnitude higher than Cockcroft and Walton were achieving. By observing the deflection of these particles in a magnetic field, they were able to confirm their charge-mass ratio in the same way that J.J. Thomson had weighed the electron and that Francis Aston had measured the weights of the atomic isotopes, by using Lorentz's law. Lorentz's law says the magnetic force acting on a moving charge will be perpendicular to the direction of travel and proportional to the product of the velocity of the charge and the magnetic field strength. This force then gives rise to a centripetal acceleration equal to the velocity squared divided by the radius of the particle's circular path. Using F equals ma, we can then say the Lorentz force must be equal to the mass times the centripetal acceleration. Dividing both sides by mass times velocity gives the relation that velocity over radius equals magnetic field times the ratio of the particle's charge to mass. As Blackett analyzed the tracks in his pictures, measuring the radius of curvature and calculating their energies, charges, and masses, he found a puzzling thing. There were some particles that had the same mass as an electron, but were bending the opposite way in a magnetic field, as if they were positively charged. Cautious as he was, he waited to publish this result until he amassed more examples of these particles. But in the end, he waited too long. In September of 1932, Carl Anderson, working independently halfway around the world at Caltech, published a short article describing the same kinds of tracks in a similar cloud chamber that he had designed in collaboration with Robert Millikan. Blackett had been scooped. Blackett rushed to publish his set of 15 photographs in March of 1933 and beat the actual publication of Anderson's pictures by a matter of days, but Blackett had to acknowledge the priority of Carl Anderson's claim to finding the positive electron, and it was Anderson that was awarded the Nobel in 1936 for discovery of what came to be called the positron, the first antimatter particle. But in 1948, Blackett was also recognized for his overall work on cloud chambers and cosmic rays. The discovery of the positron confirmed a 1931 prediction by Paul Dirac that antiparticles could exist. This prediction came from the energy-momentum relation for relativistic particles, that is, particles moving close to the speed of light. Near the speed of light, a particle's mass will increase according to Einstein's theory of relativity. The energy-momentum relation can be derived from this equation by using E equals mc squared to convert relativistic mass to total energy and the rest mass of the particle to the rest mass energy, and multiplying velocity times mass to get momentum. This equation for the total particle energy has a square root in the final equation, which allows for a negative square root. This yields a total particle energy which is negative. Dirac maintained that particles with negative energy could be real and calculated the properties of what we now call antiparticles. Particles and antiparticles have opposite electric charge and can annihilate each other, turning into pure energy. This works the other way too. Simply provide enough energy and you are able to create any particle along with its antiparticle. And so, with the discovery that antiparticles were real, it was off to the races for physicists investigating higher and higher energies to see what kinds of particles and antiparticles could be created. The early advantage in this race went to the cosmic ray chasers, who, if they were patient and clever enough, could capture cosmic ray events of almost unlimited energy. The challenge was that the higher the energy, the rarer the event. Anderson's solution to this problem was elevation. By moving his cloud chamber apparatus from Pasadena, California to Pikes Peak in Colorado, he gained more than 4,000 meters of elevation and found that he could speed up his particle detection by almost 30 times. He was also able to capture events with higher particle energies, including some above 400 MeV. This advantage in high-energy sampling allowed Anderson to claim the next new particle discovery in 1936. A negatively charged particle was about 200 times heavier than an electron, only 1/9 the mass of a proton. So where did that fit in with the existing atomic theory? Or as Isidore Rabi asked his fellow theorists in frustration, who ordered that? While the theorists were puzzling over the particle that we know today as the muon, the experimentalists had been busy working to artificially accelerate particles to ever higher energies. At the Cavendish lab, progress continued to be made on improving the Cockcroft-Walton design. Australian Mark Oliphant built a second-generation device that achieved 600 keV, and later a 1 MeV device was commissioned from the Philips company. Initially, he focused on extending Cockcroft and Walton's work with proton acceleration. Oliphant was able to force his higher energy protons inside the nuclei of not just lithium, but also heavier atoms such as beryllium, boron, and fluorine, transmuting them into other elements. He then tested proton bombardment of even heavier elements like aluminum, iron, gold, uranium, but his protons were not energetic enough to overcome the electrostatic repulsion of nuclei with such large positive charges. By 1934, Oliphant, working with Paul Hartek, had shifted from using ordinary hydrogen as a source gas to feeding heavy mass 2 hydrogen called deuterium into their accelerator. In this way, they achieved the first experimental demonstration of nuclear fusion, fusing 2 heavy hydrogen atoms together to form helium and measuring the immense energy released by that reaction. They also created 2 previously unknown isotopes, helium-3 and hydrogen-3, which is also called tritium. These successes led to similar particle accelerators being installed in many labs around the world, effectively kicking off the era of high-energy physics. Unfortunately, it was difficult to continue to scale this design to much higher than 1 MeV due to the risk of breakdown in the electrical insulation of these extreme voltages. Luckily, in parallel, Ernest Lawrence at Caltech was developing his cyclotron concept, which used Lorentz forces to accelerate particles in a spiral path and repeatedly pulse them to higher energies with relatively lower voltages. Lawrence began with a calculation of the orbital frequency of a particle forced into a circular path by a magnetic field. This frequency, or equivalently the number of orbits a particle could make in 1 second, is given by the velocity divided by the orbit length of 2 pi r. Comparing this to the equation we derived earlier from Lorentz's law, we see that the frequency is also equal to the magnetic field over 2 pi times the charge-mass ratio. When Lawrence first did this calculation of what is now called the cyclotron equation, he exclaimed to his lab mates, "The R's cancel! The R's cancel!" Because of this cancellation, the orbital frequency in a uniform magnetic field will stay constant, regardless of the actual velocity of the particle or the radius of the orbit. The trick of a cyclotron is to use an electric oscillator whose frequency is tuned to the orbital frequency, so the electric field gives the particles a series of accelerating kicks in phase as they go around. Although each kick is small, the effect is cumulative, with the particles spiraling outward at greater radius as they gain energy. The only limit to the particle energy is the physical limitation of the magnet being used. The larger and stronger the magnet, the better. Lawrence directed his student Stanley Livingston to build the initial 4-inch diameter cyclotron prototype for his 1931 PhD thesis. This device generated 80 kilovolt protons with a 2 kilovolt power supply. Months later, they had an 11-inch device generating 1,000,000 electron-volt protons with only a 3 kilovolt power supply. Based on these successes, a series of larger cyclotrons were built in successive years, culminating in a 184-inch cyclotron designed to reach 200 MeV, which started construction in 1941. Using these cyclotrons, the Berkeley Radiation Lab was able to outpace the discoveries of the Cavendish Lab and others. But the first major discovery was a bit serendipitous. In 1937, a visiting Italian physicist, Emilio Segre, asked to have a piece of molybdenum foil that had been used as the cyclotron's beam deflector. It had been bombarded by many high-energy protons. Molybdenum has an atomic number of 42. When the foil was analyzed back in Italy, however, traces of a never-before-seen element were found, later named technetium, which filled a long empty spot in the periodic table at atomic number 43. It was now clear that the cyclotron could be energetic enough to force protons into even very heavy elements to shift their atomic number. By 1940, Lawrence's lab had used their cyclotrons to transmute uranium into the new heavy elements of neptunium and plutonium. The publication of the discovery of protonium was put on hold, however, due to events in Germany. In 1938, research by the Germans Otto Hahn and Fritz Strassmann showed that the bombardment of uranium by neutrons resulted in the creation of much lighter barium atoms. They exchanged letters discussing these results with their colleagues Lise Meitner and Otto Frisch, who had recently been forced out of their research positions in Germany for being Jewish. They concluded that the only explanation was that the neutron bombardment had caused the uranium nucleus to split into two halves. Due to Nazi political pressure at the time, it was unwise for the Germans to jointly publish an article with their Jewish colleagues. So it was decided that Hahn and Strassmann would publish the discovery of uranium decay with barium byproducts, and Meitner and Frisch would publish the conclusion this was a new type of nuclear reaction, nuclear fission. Leo Szilard had left the University of Berlin for England in 1933 after Hitler had become chancellor. He was searching for ways to use nuclear reactions for power generation, although most scientists, including Rutherford, believe this to be impractical. Motivated in part by a desire to prove Rutherford wrong, Szilard came up with an idea for a self-sustaining nuclear chain reaction that he patented in 1934, but was kept secret by the British government. As war in Europe became imminent, he relocated again, landing at Columbia University in 1938. After news of nuclear fission reached America, Szilard realized this might be just the nuclear reaction to make his patent come to life. He repeated the experiment of bombarding uranium with neutrons and discovered that during the fission reaction, additional neutrons were released. He knew then that his atomic chain reaction idea would work if those neutrons could be made to split enough additional uranium atoms before escaping. This chain reaction might be a slow one that could be harnessed for energy production, or occur very rapidly in a violent explosion of unprecedented size. He began working with Enrico Fermi on experiments to demonstrate the first possibility, but he became increasingly worried about the latter. After discussing these possibilities with his fellow Jewish emigre, Albert Einstein, now at Princeton, the two of them wrote an urgent letter to President Roosevelt, warning him about the possibility of the Germans making an atomic bomb and recommending the American government start its own program. At first, it was thought that several tons of uranium would be needed for the critical mass to achieve detonation, making a bomb impractical. But that would soon change. By 1940, Otto Frisch had emigrated to England with the help of Mark Oliphant. Oliphant at this point was working with the British government on top-secret radar development for the war effort. But German expats couldn't get the level of clearance needed to join that work, so Oliphant paired him with another Jewish-German transplant, Rudolf Paes, to continue working on uranium fission, which was not yet considered a war project. The two of them soon had the insight that if uranium could be purified to its 235 mass isotope, an explosive chain reaction might be possible with as little as a pound of material. In hindsight, their estimate was about 10x too optimistic, while a similar calculation done by the leading German scientists was about 10x too pessimistic, leading the two sides in the war to have a very different sense of urgency for an atomic bomb project. Oliphant delivered a top-secret memorandum to the British government detailing the calculations of this critical mass and its explosive potential, and recommended that the Americans be informed. When Oliphant later traveled to Washington, he lobbied to make sure the memo reached Roosevelt's desk, and then visited Berkeley to make sure Ernest Lawrence understood the importance of this line of research. At this point, you should probably go watch the movie Oppenheimer, but rather than end this episode on a cliffhanger, I'll spoil it for you by telling you the Manhattan Project was successful, and after the war, big-budget nuclear science was deemed critical to national security. In the decade after the war, there was a massive increase in experimental research, which led to the discoveries of so many new subatomic particles that theorists trying to explain those results couldn't keep up. But that's a story that will have to wait for next episode. That's all for now. Thanks for watching.